This is Strategy-Proofness-Exposing Mechanism Descriptions. I'm Clayton Thomas, and this is joint work with Yannai Gonczarowski and Ori Heffetz. So I'll mostly talk in this talk about matching mechanisms. These are algorithms matching students to schools or doctors to hospitals, workers to firms, etc. These are really widespread mechanisms. And in these settings, students report their preferences over the schools, also known as their types, which I'll write as TI. These are ostensibly a list of the students' favorite, second, third favorite, and so on school. And we have this classic mechanism design environment where the preferences TI at the beginning are known only to the students. And thus, we get this classic mechanism design constraint where the students have really strong incentives to get into a good school. They really want to maximize schools for themselves. So we'd like a strategy-proof mechanism. What does this mean? Let's not read out the math, but let's just say, so strategy-proofness means that what a student I gets reporting their true preference list, TI, is at least as good, according to that true list TI, as anything they could get under any alternative TI prime that you might think of as a lie. And in theory, one great thing about strategy proofness is it greatly simplifies participation. Just straightforwardly ranking your schools from favorite to least favorite order is your best strategy if all you want is to get into your favorite school. So in this talk, we love strategy proofness. We want strategy proofness, but we want to do even better. We want strategy proofness that is easy to see. And why do we want this? It's because despite theoretically leaving no room to strategize at all, in practice, we see people playing their theoretically dominated strategies. For one salient example, they might rank a safety school higher than they actually want it in a strategy-proof matching mechanism. So a pretty big thrust in the literature lately, the theory of so-called obvious strategy proofness, has looked at this issue and then argued that some interactive mechanisms might better convey strategy proofness than others. For example, an ascending price implementation of a second price auction might do better than sealed bid. Unfortunately, it turns out that OSP mechanisms are quite rare, and they're almost completely impossible for most real-world school choice mechanisms, as a pretty big body of literature has shown. So our biggest departure point from the idea of obvious strategy proofness is not to think about different interactive mechanisms for a given social choice rule, but to think about different descriptions of the same mechanism. In particular, every mechanism in our paper remains direct revelation. And just think of the following timeline. The students start out seeing some description of what the mechanism is actually going to be. The mechanism designer really coaches them through how it's going to work. And then they all simultaneously report their preferences, their types, to the mechanism. So towards this goal, what our paper does is we propose a framework for describing direct revelation mechanisms. This framework describes things to one player at a time, so I'll tell one student at a time what they're going to get. And it makes strategy proofness hold via an easy, universal one-sentence proof. For any description in our framework, this one-sentence proof shows strategy proofness. In our paper, we try to take a quite broad look at this framework. We propose new descriptions for canonical mechanisms in different settings, for auctions, for voting, and for matching. We use a novel theoretical framework to reason about the simplicity of descriptions in this new framework. And we use a laboratory experiment to investigate this framework into more elementary mechanism design settings. But for time in this talk today, I'll focus on the theoretical results, and I'll focus on the main theoretical domain of application, matching mechanisms. I'll start by just asking a kind of high-level question that I think is really interesting. I'll just ask, do traditional descriptions of canonical matching mechanisms naturally expose their strategy proofness? And in part 1 of the talk, I'll just investigate this question for 3 canonical mechanisms. In part 2, I'll finally introduce our general framework. I'll motivate it using the story from part 1, and then finally I'll give our main positive result, which is going to be a new, simple, strategy-proofness-exposing description of the most popular matching mechanism in practice. Okay, part 1, a story of 3 mechanisms. Mechanism 1, serial dictatorship. So recall we're matching students to schools, and every student reports a type TI, which is a ranked list of the schools. But I'll clarify, so schools in my whole model are non-strategic. They don't submit preferences. They don't have their own desires about which students they get. Serial dictatorship, this is an extremely simple mechanism, but still quite useful in some settings. And what's relevant for us today is it's extremely easy to recognize as strategy proof. It might only take you 2 minutes to get through a formal proof in a lecture. So how does serial dictatorship work? It says in a fixed order, students are chosen and they're permanently matched to their top ranked remaining school on their directly reported preference list. So first student 1 will pick from the whole set. We'll pick for them using their preference list. Then student 2 will pick from the remaining seats, student 3, etc. And to see serial dictatorship is strategy proof, just observe, if I'm a student I's list can't affect the set of remaining schools, and student I's true preference list will select their favorite remaining school from this set, their favorite obtainable school. So writing down this classic definition of strategy proofness from earlier, this observation A here kind of says both sides of this equation pick from the same obtainable set of schools, and B observes that your true preference list TI will pick the best thing for TI just by definition, by construction in the algorithm. But let's even drill in a little deeper. Let's think, what did we use in this proof? We used the fact that SD calculates some set without touching student I's type, without using it. It matches I to their favorite school in this set, now using I's type. And then it just continues calculating the rest of the matching in any fashion it likes. The only thing I want to observe here, just look at this slightly generalized outline and see it is indeed vastly more general than serial dictatorship. Okay, we've seen a simple case. Let's move on to a more complicated mechanism, top trading cycles. Now, let's say each student starts owning or endowed with one school. Let's say student I starts endowed with school I for each I. It generalizes fine to other settings in the paper, but just for simplicity in the talk today. So if each student starts endowed with some school, TTC is some canonical mechanism for kind of improving the matching, getting students to things they like even better. And its strategy proofness is naturally more complicated than SD, the super simple mechanism, but it might take you only 15 minutes to give this proof. So how does TTC work? So students trade their endowed schools in cycles. This means each student I points to the student endowed with their favorite remaining school. In this graph, where there's out degree 1 at every single node, you can think for a little while and see there has to be some cycle in this graph while everyone's pointing. So pick any such cycle, permanently match the students to the school they point to, and recurse. And there's this known lemma that we're going to use. This lemma says TTC is independent of the order in which I choose and match these cycles. It doesn't matter which ones I pick, I'll get to the same thing at the end of the day. And kind of proof by example of this, so here we can see it doesn't matter if I matched 5 and 6 first or 2 and 3 first, I get to the same remaining set at the end of the day. This is indeed not that involved of a consequence of just the observation that no 2 cycles can actually overlap when there's just out degree 1 everywhere. So here is one method of seeing that TTC is strategy proof, given this lemma that it doesn't matter the order we pick cycles. So fix my favorite student I, and consider the following run of TTC. First, as long as possible, match only cycles that don't involve student I. Equivalently, I can think of I doesn't point, but other people point to I, and we only match cycles that don't involve I. Now I can observe wherever I points, whatever is the favorite remaining thing of I, this must complete a cycle. Once everyone points, there has to be a cycle, so I must complete it once I start to match them. So when I match I, I'll be matching them to their favorite remaining school. I can do this, I can match the whole cycle they're in, and then I can just continue running TTC in any order you like. This is one run of TTC specialized to student I. So what did I do here? Our theorem formalizes this argument to say one run of TTC, A matches all cycles not involving student I, B matches I to their favorite remaining school, and C calculates the rest of the matching via sum method. But this just directly implies TTC is strategy proof by exactly the same simple proof outline as in serial dictatorship, just copy and paste it. Student I's list can't affect the set of remaining schools calculated in step A, and student I's true preference list will select their favorite obtainable school in step B. So this is the story so far for SD and TTC. Let's move on to actually the most important mechanism of the talk and of the paper, deferred acceptance. So now in the model, each school has non-strategic priorities over the students. Mathematically, these are going to be identical, just symmetric with the preferences of the students, but we think of them differently. We think of them as fixed and non-strategic, say determined by policies like the address of the student, etc. DA is a very canonical mechanism. It calculates stable matchings with respect to the preferences and the priorities. There are many reasons people really like it in practice. I'll skip them, but they've led for it to be the most common strategy-proof matching mechanism in practice. Unfortunately, despite these beautiful properties, its strategy proofness can be quite challenging. If you're giving the formal proof to undergrads, it might take you more than a lecture to get through the mathematical proof of strategy proofness of DA. So how does DA actually work? Its traditional description is this classic student proposing deferred acceptance algorithm. Students propose in order of their preference list. Schools keep the highest priority favorite proposal they've seen so far, possibly rejecting tentative acceptances from previous rounds. And you just continue doing this, going down students' preference lists until everyone is matched or has proposed to their entire list. What I find really, really fascinating about this algorithm, it's beautiful for a lot of reasons, but I find it fascinating that this algorithm is explained in detail to everyday non-expert people. I can't really think of a more complicated combinatorial algorithm that policymakers try really hard to convey to just regular people, such as parents and students. As we can see from two examples here, both kind of related to the NRMP, one of the most famous usages of deferred acceptance. So what does our result say informally about TTC, about DA? How does DA fit into this story? How does it relate to TTC and SD? So recall that we showed kind of within the traditional description of TTC, we found one outline for exposing strategy proofness. We found this ABC description. For some student I, calculate what you might get without using your type, match you to your favorite thing in that set, and continue. Our main impossibility result is going to say this isn't the case at all for DA. We're going to say nothing close to the traditional description of DA could possibly fit in this three-step ABC outline. So first, very crucially, we need to model what is close to traditional DA. First, DA is student proposing. It reads students' preferences once from favorite to least favorite order without restarting or going back at all. Second, DA only remembers and does any bookkeeping for a single tentative matching of the students to the schools. Maybe storing a little bit of extra metadata, the set of currently unmatched students, or the number of proposals students have done, things like this. But regardless, it's only roughly linear memory in the number of students, much lower than the n² memory required to remember every student's list, and indeed roughly as low as possible since it's the size of the output. The matching we're trying to find at the end of the day is only O of n bits roughly itself. And I'll remark and try to emphasize, so while this is kind of computational in nature, we're really not worried at all about how the school district is going to run DA on their server at the end of the day. These are trying to capture aspects of how DA is explained in practice, like in these nice videos. So what does our result say? With this formal model, our result says that any student proposing algorithm for DA fitting this three-step outline: A, calculate the set of options I can have, B, match I, finally using their list, C, calculate the rest of the matching for all the students, including those other than I. We prove that any student proposing algorithm for DA with this three-step outline requires memory omega n², nearly matching the memory requirement of just memorizing the entire input. And if you hand me some algorithm using that omega n² memory, I'm not sure exactly what it's doing with all of its memory, but it's definitely not just going to be tweaking a tentative matching as it goes. This is way far off from just the linear memory of traditional DA storage. It's doing something requiring a lot more bookkeeping or rote memorization. So a direct interpretation of this is kind of no small modification of DA could reveal strategy proofness via this ABC outline. But kind of what I think was really interesting about it is putting it in the context of SD and TTC. For SD, our life was great. We could explain strategy proofness, and we could explain strategy proofness to all students at once, simultaneously with the traditional description. For TTC, this wasn't quite possible, and in fact, the description has to kind of be specialized to each student separately. But conditioned on this, our life was as nice as possible. A tiny little modification of the traditional description of TTC sufficed to convey strategy proofness via this canonical ABC outline. For DA, unfortunately, it turns out this is just very hard. Like, nothing close to traditional description of DA makes this ABC framework for exposing strategy proofness apparent. The data structure needed to store that is just not there along this process to arrive at the matching in DA. And for just a brief slide on the proof, I won't really read this, but if you want to pause the video, here's a short proof sketch to kind of illustrate how the omega n² bound really starts to show up, is with these green arrows here visually in the proof sketch. Okay, so that concludes that almost concludes the story part of the talk. So this was bad news. This was an impossibility result for DA. We proved that you can't fit this three-step outline ABC. What do we do? What do we do given this bad news? Well, here's one idea. Simply throw away step C. Abandon trying to calculate the rest of the matching for everyone and just expose strategy proofness to student I. This new outline using only A and B is going to describe only I's match, but also expose strategy proofness to student I. So that brings us into part 2, strategy proofness exposing mechanism descriptions. So here's our idea, throw away step C, what do we get? Step A uses only T minus I, the reports of students other than I, to calculate a set of schools student I might receive. Step B uses TI, I's report, to award I their favorite school from this set. It's not too hard to see that there's only one set that the thing in step A can really be. And let's call it the menu of student I, defined by T minus I, everyone else's report. This is the set of schools that I might possibly receive holding fixed T minus I, just looking over all the possible reports of student I. And since this is called the menu, we call this framework a menu description for student I. What makes it great is that strategy proofness holds by exactly the same simple proof outline I've been giving throughout this talk. Student I's report TI can't possibly influence the set in step A, and in step B, student I's true preference list TI will select for them their favorite obtainable school. And this finally brings us to the first premise, the starting point of the paper. In this sense, menu descriptions are one way to expose strategy proofness. The first thing to observe about menu descriptions, though, is that every strategy proof mechanism has a menu description. For example, just take any algorithm for calculating the matching itself, calculating the mechanism. One menu description just says, look at all of the possible TI primes in the entire universe separately, run A on TI prime T minus I, add the result to some set M, and B, allocate I to their favorite outcome in M according to their reported type TI. You might call this a brute force menu description. Unfortunately, this brute force description doesn't seem very plausible. This seems quite a far cry from the algorithms people actually explain in practice, such as traditional DA or even TTC. In practice, what we would want are simple and natural mechanisms, natural algorithms. And this brings us to the second premise of the paper, that brute force descriptions such as this, or any generally complicated description, these are really undesirable. Instead, we should look for simple menu descriptions, likely via context-relevant, possibly subjective notions of simplicity. And indeed, the impossibility theorem I've already presented in this talk, this rules out one category of simple descriptions. This is some formal way to measure simple descriptions. But the description I'll present next in the main positive result of the paper, we view this description as kind of subjectively, intuitively simple. Even though it also satisfies certain formal properties, I really think inherently for descriptions, the best way to evaluate them is always going to be kind of inherently by the viewpoint of an individual person. Yeah. So given all this, here's a slide for related work. I won't read it for time's sake, but here, if you want to pause, is some theoretical related work and empirical related work as well for some of the things I won't get to in this talk. All right, with all this, we can go to the main positive result of the paper, a menu description for deferred acceptance. So here's our menu description of DA. I'm going to tell you who you will match to. Step A, if we hypothetically run school proposing DA without you included in the market, you will earn admission at every school that prefers you to their hypothetical match. Step B, you'll match to your highest ranked school where you earn admission. So what we're doing here is we're using school proposing DA without you to describe your own match. But our main theorem says this is a description of student proposing DA. We're going to describe your match in student proposing DA, despite the fact that we use a school proposing algorithm. And in particular, closely related to this, it turns out that the hypothetical match of the other students from step A can sort of be almost unrelated to their actual match at the end of the day in the mechanism. So let's think, so what does this description actually do? First, it seems nearly as kind of algorithmically simple as traditional descriptions, again, according to intuitive notions. It's just a single run of some version of the DA algorithm with the sides flipped, along with this, hopefully even kind of intuitive menu defining and picking step. In stark contrast to traditional DA, though, its strategy proofness is easy to show. By the same proof outline from before, my report can't affect the set in A, and reporting my true preferences gets me my favorite obtainable school in B. So with this description, you can replace advice that might say famous economists have proven you shouldn't strategize with just this same simple proof outline that you can describe in explicit detail to ordinary people, hopefully. So more concretely, what does adopting this new description do? Under traditional DA, we had a nice description. It explained a lot of things, the fact that the matching was one-to-one and maybe even stable. But these things are kind of mostly the concerns of the policymakers, the people who wanted to select the matching. What our new description does is explain strategy proofness, the most crucial thing that a student needs to know when formulating their own preference list, their own report to the mechanism. In the paper, we kind of investigate this trade-off between exposing the matching and exposing the fact that it's one-to-one with exposing strategy proofness. And we prove that this trade-off is unavoidable for a pretty broad class of simple descriptions. This requires additional modeling that would take far too long for this talk. For example, to rule out school proposing descriptions with the ABC outline. But we take an in-depth look at that in the paper, and we indeed prove a pretty broad trade-off. You can either choose to expose one-to-one, or you can choose to expose strategy proofness. The proof, again, I won't read, but it isn't super involved. In fact, this is the entire proof, not just a sketch. It just uses some classical properties of stable matching that may be familiar to some people. And we provide two proofs, one fairly clean one here on the slide, and an alternative one that avoids using the strategy proofness of the traditional description of DA, thus providing a semi-alternative route to proving the strategy proofness of that traditional description. Prove it's equivalent to this menu description, and then strategy proofness holds directly. All right, quickly wrapping up. So our result gives a new, simple strategy proofness exposing description of canonical mechanisms. In the paper, we look at other settings. We take a look at fairly simple auctions, and we do a laboratory experiment in two simplified settings, a second price auction and a median voting mechanism. We are iterating on this framework in a few ways. We have a theoretical follow-up looking at different notions of complexity or simplicity for matching mechanisms. And we have an in-progress empirical follow-up work bringing these experiments to the menu description of DA. And this requires vastly more involved lab settings than our simple mechanisms, second price and median voting, and thus is going in a follow-up work. I really like this direction still after working on it for a while, but I really think that more formal theories of explainability are needed, and really impossibility results can help to guide the way towards new ideas, new avenues, as I hope I hinted at throughout this talk. Thinking about what you can't do can really guide you, and I'm excited to see where that goes. Yeah, thanks.